So hello everyone. So today we will be starting enzyme inhibition part in this module 3. So if you quickly revisit in the last lecture we discussed about enzyme activity, and enzyme activity is basically it is related with the rate of enzyme activity, and enzyme unit is the measure of enzyme activity. In fact, we also discussed the specific activity, and activity is divided by the mass of the protein. In addition, we discussed how to evaluate kinetic parameters. So, we discussed this Michaelis-Menten equation can be rearranged in a Line-Weaver-Burk plot, hence Wolf plot and Eddy-Hofstee plot. So, in this way we have to have this y and this is x, this is y, this is x, and this is y, this is x. So, once we plot y to mx plus c, so basically we take this slope and intercept to decipher kinetic parameters. So, today we are going to discuss about this enzyme inhibition. So, we will be seeing there are two kind of enzyme inhibition, reversible and irreversible. So, first we will see the reversible inhibition, particularly competitive, uncompetitive and non-competitive inhibition. Then we will see how we should be able to calculate the kinetic parameter in the case of enzyme inhibition. So, why we need to regulate the enzyme activity? As we know, the enzymes are biocatalysts for any biochemical reactions, and metabolic pathway have n number of biochemical reactions. So, if you want to regulate the throughput of any biochemical reaction, we need to regulate through the enzyme activity. So, one way is to go with the synthesis of protein, means we are going to either induce or repress the transcription and translation part, so that we can have less or more synthesis of proteins which act as an enzyme. But however, it does not provide rapid response. So, what is the alternative for this? Alternative for this is we can use some metabolites and other effector molecule which can interact with the enzyme molecule to alter its catalytic property. How it is going to alter? They can alter the availability of active site for the reaction, they can alter the affinity of substrate for enzyme binding, they can alter the ability of enzyme to form and release the product. So, it can, your molecule can target to the E, it can target to the ES. Now, when you are using this approach, so this approach we call it enzyme inhibition. Rather than this going for transcription and translation, one way to regulate is to use the enzyme inhibitors. These interactions allow the activity of enzyme to be altered relatively quickly. So, we can get a quick response as compared to this transcription and translation. Now, we can define what is the inhibitor. Any molecule that reduces the rate of an enzyme reaction is called an inhibitor. Now, it may be your reaction product, it may be your substrate analog, it may be any synthetic molecule, it may be metabolic intermediates, or it may be heavy metals. So, these are a few examples of enzyme inhibitors. Now, as I told initially, this binding between inhibitor and enzyme may be reversible or irreversible. So, we call reversible inhibition and irreversible inhibition. So, now we can summarize what is enzyme inhibition. So, enzyme inhibition refers to the decrease in the enzyme activity due to its interaction with specific molecules or inhibitors. Now, inhibitors can interfere with substrate binding or catalytic activity. So, inhibitor can, if you remember, we have E is binding with S, forming enzyme substrate complex. This is going to the E plus P product. So, inhibitor can target E, inhibitor can target ES. Enzyme inhibitors, molecules that interfere with catalysis, and particularly the slowing or stopping enzymatic reactions. So, what is its biological response? Since enzyme catalyzes all biochemical processes, inhibitor can significantly impact metabolism and function. In fact, many important drugs are enzyme inhibitors. So, we can stop any metabolic process or metabolic pathway. For example, aspirin. We take aspirin, it inhibits an enzyme involved in prostaglandin synthesis, which is linked with pain and inflammation. So, in this way inhibitor can also be used for a given application. In addition, there are other roles of inhibitor, that is to reveal the mechanism of enzymatic reaction, and it also help to identify and map certain metabolic pathways. Now, this interaction between enzyme and inhibitor may be reversible or irreversible. Reversible will say when this interaction is through non-covalent bond, and this effect is temporarily and can be reversed. And as I told initially, there can be competitive inhibition, non-competitive, uncompetitive and mixed inhibition, and these we are going to discuss in today's lecture. In addition, there is irreversible when there is a tightly bound through covalent interaction and it permanently inactivates the enzyme. It often involves modification of amino acid residue at the active site. So, once active site has been altered, your enzyme becomes non-functional. Example, penicillin inhibits transpeptidase, which is required for the bacterial cell wall synthesis. In this way, it acts as an antibiotic. Aspirin, it acetylates and inactivates cyclooxygenase. So, in this way they are permanently inactivating the enzyme through covalent interaction. So, as I told, we are going to discuss competitive, non-competitive and uncompetitive inhibition. So, enzyme is binding with the substrate to form enzyme substrate complex, it further dissociates into enzyme and product. So, in the case of competitive, so here inhibitor can either target to the enzyme or inhibitor can target to the enzyme substrate complex or it can target to both. So, in the case of competitive inhibition, inhibitors bind only to the free enzyme, not to the enzyme substrate complex. So, you just see inhibitor is binding with enzyme and forming an enzyme inhibitor complex with dissociation constant Ki. Now, how it is able to bind? You just see it is having the substrate homology or analog. So, the way substrate can fit here, your inhibitor can also fit here, and if it is, you just see a lock and key model. So, because of the molecular similarity with the substrate, inhibitor can bind to the active site of an enzyme. So, as you remember, this enzyme on substrate, the Michaelis-Menten dissociation constant Km is defined as K minus 1 upon K1. K is the K catalytic and Ki is the inhibitor dissociation constant. So, one example is succinic acid is converted to fumaric acid and enzyme is succinic dehydrogenase. Now, if you just see the structure of succinic acid and malic acid, it has COH group at the both the terminals, COH group at the both the terminal. So, it is able to bind at the active site of succinic dehydrogenase, so that it can inhibit the synthesis of fumaric acid. Now, again for this competitive inhibition, one can use this Michaelis-Menten equation to define the enzyme kinetics. What is difference here? The only difference comes, the Km is increased here. The Km becomes Km 1 plus I upon Ki. So, basically here Km has increased, or you can say Km dash equals Km 1 plus I divided by Ki. So, here Km has increased, and if you define this as Km apparent, so you can write the similar expression V equals V max S upon Km apparent plus S, and Km apparent is Km 1 plus I upon Ki. So, here you can say there is no change in the V max and Km has increased. This value is higher than the Km. So, if you plot substrate versus velocity, so this one is the typical Michaelis-Menten equation in the absence of any inhibitor. So, if you just see what is Km when V equals to the V max upon 2. So, if I put V max upon 2 here, and corresponding value of substrate is the Km. In the case of inhibitor, it has delayed, and if I again calculate the Km, so Km has increased. So, what it says is Km dash is greater than Km. How to overcome this? If you just see at the initial substrate concentration, there is difference in the rate, but as you increase the substrate concentration, you cannot observe the significant change in the rate of enzymatic reactions. So, increasing substrate concentration overcomes competitive inhibition. So, again I repeat, V max is not affected since your inhibitor is not interacting with enzyme substrate complex and Km value is increasing. Next, we are discussing non-competitive. As the name suggests, non-competitive. So, non-competitive inhibitors bind with free enzyme or enzyme substrate complex. So, it can bind to either, it can target enzyme, it can target enzyme substrate complex. The inhibitors bind to the site other than the substrate active site, and thus independent of the presence or absence of substrate during the reaction. This action results in conformational change in the protein that affect the catalytic step, and hence decreases or eliminates enzyme activity. If I say it decreases or eliminates enzyme activity, means it is interfering with the product formation or rate of reaction of enzyme. For example, heavy metal poisoning HCPB distorts the SH group containing enzyme at allosteric site. Doxycycline is a non-competitive inhibitor of proteinase enzyme in bacteria. So, when we say non-competitive, it means it is not binding to the active site, but it can bind to both enzyme and enzyme substrate complex. And as it is binding to both enzyme as well as enzyme substrate complex, so it is going to affect V max, rate of reaction. So, basically the rate of reactions will be decreased. So, if you remember what is the value of V? V max is defined as K catalytic into E naught, and in the presence of inhibitor it becomes V max apparent. So, V max will be there divided by 1 plus inhibitor concentration divided by inhibitor dissociation constant, I divided by I plus Ki. So, here in case of non-competitive inhibition, the V max has become apparent V max, or you can say there is decrease in the V max value. So, if I draw this Line-Weaver-Burk plot, so in the Line-Weaver-Burk plot we have 1 upon S, 1 upon V, intercept is 1 upon V max, and as we are saying V max has decreased. So, in the presence of inhibitor, you can see this is the line for the non-competitive inhibition, where the value of 1 upon V max has increased here, because there is a decrease in the V max value, while the Km is unaltered and V max is the lower. Next, we will discuss uncompetitive inhibition. In the case of uncompetitive, the inhibitors bind only to enzyme substrate complex here. So, you just see once enzyme substrate is there, it forms enzyme substrate complex, and now inhibitor is binding this enzyme substrate complex here with a dissociation constant of Ki, and in this case what is happening, once it is binding, it is affecting both the value of K as well as the value of Km. So, both are lowered now, because some part of ES is going to ESI. So, it is affecting both product formation as well as this Michaelis-Menten dissociation constant. So, both are lowered now. So, Km become Km apparent, Km divided by 1 plus I upon Ki, and V max become V max apparent, where it is V max divided by 1 upon I plus Ki. Still we can write in a similar expression like Michaelis-Menten equation. It says V equals V max apparent S divided by Km apparent plus S. So, you just see an uncompetitive inhibitors bind at a site distinct for substrate active site, and here it is affecting both V max and Km, both are decreased. So, V max is the lowered, you just see here, and Km is also lowered in the presence of inhibitor. So, and as we know, this V max apparent is V max divided by 1 plus I upon Ki. So, in this figure I upon Ki is represented as alpha, and you can see there is an increase in the value of alpha, there is a increase in the inhibition. I have listed a few examples for uncompetitive, that like drugs to treat the cases of poisoning by methanol or ethylene glycol acts as uncompetitive inhibitors. One more example is tetramethylene sulfoxide and 3-butyl thiolene oxide are uncompetitive inhibitor of liver alcohol dehydrogenase. So, for the liver alcohol dehydrogenase, tetramethylene sulfoxide and butyl thiolene oxide are uncompetitive inhibitors. Now, if you can summarize here, so what we are seeing here, if you plot Line-Weaver-Burk plot for all three cases, competitive, uncompetitive and non-competitive inhibition. So, in the case of competitive, what we have observed is Km has increased. So, Km apparent has become Km 1 plus I upon Ki. In case of uncompetitive, V max Km is reduced and V max is reduced, because this is targeting to enzyme substrate complex. So, here V max is V max apparent V max divided by 1 plus I divided by K I, and Km apparent is Km divided by 1 plus I upon Ki. In the case of non-competitive inhibition, Km remains unaffected and Vm is reduced like Vm divided by 1 plus Vm apparent Vm divided by 1 plus I upon Ki. Now, we will see a couple of examples based on these three concepts. So, here a single substrate enzyme catalyzed reaction was investigated at a fixed initial enzyme concentration and following data were obtained. So, we are having the substrate concentration S and we are having the velocity in the presence of different inhibitor concentration 1, 2, 3, 4 and 5 millimole per liter. Now, we have to comment the nature of enzyme inhibition. So, what we have to do? We have to calculate the value of Km as well as the V max, then we should be able to comment on the type of enzyme inhibition. So, for this how we will proceed? We have already have some data, S is there. So, we can tabulate like this 1 upon S and 1 upon V, and we have for I is equals to, there are 5 different value of I, so 1, 2, 3, 4 and 5. Then we can plot 1 upon S, 1 upon V, and here the slope will be Km upon V max, intercept equals 1 upon V max. So, what I did, we have plotted this and I will note down the value of the slope, intercept, and once these two are there, then we can calculate Vm and Km. So, for different cases 1, 2, 3, 4, 5, 1, 2, 3, 4 and 5. The slope value is 2.62, intercept 1.19, Vm is 0.84 and Km is 2.21. In the second case, we are getting slope as 3.09, intercept 1.30 and corresponding value of Vm is 0.77 and Km is 2.37. Again, for the third case, we have slope 3.49, intercept 1.41. So, Vm has decreased further to 7.71 and Km is 2.47. In the fourth case, slope is 3.87, intercept 1.50, Vm is decreased to 0.66 and Km is 2.57. In the last case, I equals 5, slope is 4.22, intercept 1.58. So, Vm is further decreased to 0.63 and Km is 2.67. So, what we are seeing here is, I have listed here the value of Km and value of V max. So, V max value is decreasing and we can see there is a relatively less change in the Km. So, we can say Km is constant and V max is decreasing. So, V max is decreasing, Km is constant. So, this is a example of non-competitive inhibition. So, this is one example of non-competitive inhibition. So, in this way we have to decipher the kinetic parameter, then we can comment on the type of enzyme inhibition. We will take one more example. An enzyme catalyzed reaction was found to be affected by two inhibitors A and B. The initial reaction velocity were measured at various substrate concentration. You just see substrate concentration was varied from 2 to 50 millimole per liter. In the absence of inhibitor, this is uninhibited this case, and in the presence of 1 millimole per liter of either inhibitor A or inhibitor B, in the presence of inhibitor A and inhibitor B. The results are shown in table below. Comment on these results and deduce the likely nature of inhibition caused by inhibitors A and B. So, we can quickly see, if you are increasing the substrate concentration, rate of enzymatic reaction is increasing up to here. If you increase further, it is decreasing. So, this is an example of substrate inhibition that we will discuss in the next class. But as of now, let us consider up to here. If you increase the substrate concentration, the rate of reaction or velocity is increasing, and if you compare the value with 1.43 in absence of inhibitor with 1.01 in the presence of A inhibitor, 1.653 in the presence of B. So, the rate has decreased, it means there is a inhibition. Now, what we are going to do? We are again going to analyze the same thing from substrate concentration up to 2 to 10 millimole per liter. So, for substrate concentration of 2 to 10 millimole per liter, we are having 3 different cases. In one case I equals 0, there is no inhibition. In other case A is inhibitor, second case B is inhibitor. So, we will again calculate Lineweaver work plot 1 upon S and 1 upon V. I am going to note down the slope and intercept value. Slope and intercept, then from there we can decipher Vm and Km. The slope is 2.79, intercept is 0.42. So, Vmax will be, Vmax is 1 upon intercept and slope is Km upon Vmax. So, Vmax will be 2.39 and Km is 6.67. In the presence of inhibitor A, the slope is 2.58, intercept is 0.43. So, Vm is 2.35 and Km is 13.11. In presence of inhibitor B, the slope is 6.18, intercept is 0.90. So, as intercept has increased, so Vm is decreased to 1.11 and Km is 6.84. Now, we can compare. In the presence of inhibitor B, Vm is reduced, Km is unaffected. In the presence of inhibitor B, Vmax is unaffected, Km is increased. Km is increased here and here Vmax is decreased. So, if you remember correctly, as this in the presence of A, Km is increased, it is a competitive inhibition, and in the case of B, where Km is unaffected and Vm is decreased, this is a non-competitive. I can revisit the slide again. Km is increased, competitive, Vm is unaffected, and Km is unaffected, Vm is reduced, non-competitive inhibition. So, this is A is competitive inhibitor, B is non-competitive inhibitor in this case. We will have one, as I discussed earlier, from 10 to 50 millimole per liter, we are also observing there is a further decrease in the rate, that is called substrate inhibition, that we will discuss in the next lecture. One more example we can see, consider a single unisubstrate enzyme that follows Michaelis-Menten kinetics. When enzyme catalyzed reaction was carried out in the presence of 20 nanomolar concentration of an inhibitor, there was no change in the maximum velocity. It means Vm apparent equals Vm. However, the slope of Lineweaver work plot increased 5-fold. Slope has increased means what is the slope of Lineweaver work plot? Slope is Km upon Vm. It has increased by 5-folds. So, you have to calculate the dissociation constant for enzyme inhibitor complex. So, what we are seeing here is Km apparent upon Vmax equals 5 times of Km upon Vmax. So, if we already know this, what is the Km apparent? Km apparent is Km 1 plus I upon Ki. So, if you put here, so this becomes Km apparent upon Km 1 plus I. What is the concentration of inhibitor? 20, and Ki we have to calculate, and this value of Km apparent and Km is 5. So, it becomes the Ki equals 20 upon 4, or you can say 5 nanomolar. So, will this I will stop here for this lecture. So, today we discuss reversible inhibition, competitive, non-competitive and uncompetitive, and also we solve a couple of examples based on these concepts. Thank you so much.